In this video, we're going to go a little bit farther with our introduction to vectors. First idea to introduce is unit vectors. Unit vectors are vectors that have a magnitude of 1. They have no units. Have a magnitude of 1, have no units, but they do have direction. Are denoted with a hat. The vectors, unit vectors that we're going to have are going to be I hat, j hat. These are what we'll be using most of the time, and k hat if we added a third dimension. Now for us, we're not going to use the k hat vector much. But these three vectors point, the I hat vector points in the positive x direction, the j hat vector points in the positive y direction, and the k hat vector points in the positive z direction. Again, we're going to mostly be using the xy plane, so we'll just have the I hat and j hat vectors in use here. Well, what good are these things? What we can do with them is, let's suppose that we have a vector that points, I'm going to come out here to call this 6, and this will be the x direction, and maybe it's in meters. Okay, and then we'll go up. I'm using quarter inches as my unit of distance. Heavens, I should be using centimeters, but this will be 7. This is the y direction, also in meters. And let's suppose that we have a vector that looks like this. And this is a vector r. Well, I can see just by the way I drew this thing that r is going to have a component in the x direction that's equal to 6, and so I could write that r sub x, if I think of this as r sub x, we're going to drop this kind of notation pretty quickly, but it's going to equal 6 meters in the x direction. And then r sub y, I can see here, this would be r sub y. That's going to be 7 meters in the y direction. Okay. Well, there's a better way to write this, or a shorthand way to write this. I can just write the whole vector r equaling something like this. It'll be 6 meters. Now, I said that I hat pointed in the positive x direction. This is a scalar. If I multiply it by I hat, I'll get r sub x. I'll get a vector with a length of 6 meters in the x direction, because I hat has a length of 1. It points in the positive x direction. It doesn't have any units, but if I multiply it by something with units, it acquires those. That's only part of r. Plus, it's got a 7 meter vector in the j hat direction, or in the y direction. Well, if I multiply 7 meters by j hat, that's this vector. 6 meters in the I hat plus 6 meters in the j hat. This is called component form, or I think of it also as just I hat j hat form. When I ask you to write a vector in I hat j hat form, that's what I mean. So that's what they'll be. And we'll see that we can do all sorts of stuff when we've got the vectors in this form. That will be useful. Now, writing them in component form, we've already done that, but let me do something a little bit more with that. I'll do a couple of examples here. Let's suppose this is our XY coordinate system, and maybe they're not exactly perpendicular, but pretend they are. So here's y up here. And I'm just going to go with length vectors for this so we get in the habit of hanging on to the units of things. These are both in meters, not to scale here, but I'll just pick a vector and draw a vector here, and don't assume that the angles are going to be exactly correct. But let's suppose I've got a vector W here, and it points in this direction, and it makes a 39-degree angle with the positive x-axis. Okay, so W is going to be the magnitude of this vector, and let's just suppose that it's 42.0 meters. So that's the length of this vector. Right. Well, what are the components of W? Well, I can do some basic trig here. I'm going to redraw it again just because it's easier to do here. Here's my angle theta, which is 39 degrees. Let's make it 39.0 degrees so we can keep 3 sig figs on this thing. And I know that this is 42.0 meters here. Well, how much is this? Okay, this would be the I hat, or the x component of the vector W. Well, this thing divided by the hypotenuse is going to equal the cosine of theta, cosine of 39.0 degrees, which means I'll just call this the x part, or the x component. The x component, the x component divided by 42.0 meters is going to equal the cosine of theta, or cosine of 39.0 degrees. That means the x component is equal to 42.0 meters times the cosine of 39.0 degrees. Okay, that's going to be kind of common. And play around with these enough so you're getting good at just looking at something like this and being able to say, okay, this part will be 42 meters cosine of 39 degrees. This part is going to be 42.0 meters sine of 39.0 degrees. Okay. And we're going to have these things going in all sorts of different directions, so we'll have to be careful about how we happen to get these. But that means that the x component is going to be, now the y component, in my head, I'm going to think this divided by this, that's the opposite side, opposite the angle over the 42 meters, is going to equal the sine of 39.0 degrees, so that y component will equal 42.0 meters times the sine of 39.0 degrees. I got 26.4 meters. I just started with knowing the magnitude of that vector and the direction it pointed, and now I have the x and y components. I can write this vector W as the x component, 32.6 meters times I hat, plus the y component, 26.4 meters along j hat. I've got a nice representation of that. Let's add a second vector on here. Well, let's see. Start with W equaling that. 32.6 meters in the I hat direction plus 26.4 meters in the j hat direction. Okay, now I'm going to add a second vector here. Let's just pick a vector that comes up here, and this is a vector M. Don't think I've used that. And M makes a 30.0 degree angle with the positive y-axis measured counterclockwise. M has a magnitude of not 42.0 meters, but 15.5 meters. Okay, so that's its magnitude. Well, can't use the same things this time, but I can draw a pretty good triangle here and figure this out. I've got 15.5 meters out here. I've got a 30-degree angle here. Let's see. This part up here, this divided by 15.5 is the sine of 30, or this is going to be 15.5 times the sine of 30, which is 7.75, I think. Cosine of 30 I can't get so easy, but this side divided by the hypotenuse will be the cosine of 30, or this side will equal 15.5 cosine of 30, and that will be 13.4 meters. So, writing vector M in component form, I will have, now here's something tricky. Its x component is pointing in the negative direction. Well, the way we indicate that is just to take that minus 7.75 meters in the I-hat direction. That's it. That gives me a vector that's equal to this one pointing right along here that I didn't bother to draw in. It's got a positive y-hat component though, so we'll have, because it's pointing up, the y component would be, whoops. Anyway, plus 13.4 meters in the j-hat direction. And there's M. M plus W equals what? Well, here's an easy way to do that. You just take the W vector, write it right underneath this thing, 32.6 meters. I-hat plus 26.4 meters in the j-hat direction. And let's see, if I just add these together, I want M plus W. Well, 32.6 plus a minus 7.75 is going to be, I can only keep places out to the tenths place. I get 24.9. in the I-hat direction. And these two I could probably add in my head. 26 plus 13 is 39. 0.4 plus 0.4 is 0.8. So I get 39.8 meters in the j-hat direction. Okay, well, what would... No, wait. Let's go M minus W and see what that would be. Well, again, I can just write this and write that and then do the subtraction. I'm just going to write W here. I guess I could write minus W and add it, but I can also just do straight subtraction here. Minus 7.75 minus 32.6 minus 40.4 in the I-hat direction. 13.4 minus 26.4 I think is probably going to be minus 13, but I'm going to check it. Yep, it's minus 13, minus 13.0 meters in the j hat direction. That's what that vector is. Where is that going to be? Well, you can kind of sketch it. It's got an x component that's about 3 times as big as its y component. So that'll be a vector that points out this is y here and x here in meters and in meters. I don't have a decent set of diagrams here, but it'll be a long ways out in the j hat direction, and then down about a third of that, both components are negative, about a third of that down in this direction, and this is the direction of m minus w. We just figured out what that happens to be. Some people will kind of get hung up on measuring the total angle counterclockwise from the x-axis. I don't care about that. I just look at the angle it makes with one of the coordinate axes and figure it out from there. So I'm just dealing with a simple right triangle when I'm figuring out the components of these. Your calculator may give you that number, but you sort of lose intuition when you don't draw a simple diagram like that. If we make an XY plot here, vectors that are in this first quadrant have both X and Y components positive. Vectors in this quadrant, they'll have a positive Y component but a negative X component. So I'll just say pos y, negative x. Vectors down here, well, x is negative, y is negative, so they have a negative x, and a negative y. Vectors in this region, they've got a negative y but a positive x. So and just think about that when you're given values of vectors and things like that. Now, something I haven't done yet is to calculate magnitudes of any of these vectors. So let's do that. We had that the magnitude of W. It's just going to equal, these things are perpendicular to each other. They make nice little right triangles, so it'll just equal w sub x squared, its x component, plus w sub y squared, which in this case is just going to be the square root of that thing. Okay, I get about 41.9. Well, I didn't bother to write the numbers in, but and that'll be meters, because meter squared plus meter squared gives you meter squared, but you take a square root, so you get that. And m that we had over there, oh, m had a magnitude of 15.5. We already figured that out. Oh, I think we were given this. All right, that works just fine. But m minus w, the magnitude of m minus w. Now, I didn't make up a symbol to call m minus w yet, but that'll be the magnitude of this vector here. Well, I'll go ahead and write it out. M minus w. Now I have to be careful that I have the vectors on here, because if I left the arrows off that, it would mean the magnitude of m minus the magnitude of w, and that would be 41.9 minus 15.5, but that doesn't take into account that they have an angle with each other. And so to get this, you have to take the square root of minus 40.4 meters squared, and when you square that, it's going to become positive, plus minus 13.0 meters squared, and that'll become positive as well, and I get 42.4. Now, notice that the magnitude of m minus the magnitude of w would equal 15.5. Actually, we'd want the absolute, well, let's go ahead and calculate it. Minus 41.9, which is negative, I'm being lazy, I should do that in my head, minus 26.4. Okay, that's a negative number, okay, because taking the magnitude of m, which is smaller than the magnitude of w, and I get a negative number. But the magnitude, this represents the length, just the plain old length of the vector m minus w. And that's what we get. Oops, I forgot the units on there. Man, that's bad. And this is bad. And this is bad. And this is bad. Keep units at every step in your calculation. Don't talk and write like I do. Okay, that's a little bit of vector arithmetic there, and should be enough to get you started. If you supplement that with reading in the textbook, fill in some holes, I've got some suggested problems that you can do in this area.